Automation breaks where humans don't. That future depends on just one question. What kind of machine can actually function where humans work? This is where Boston Dynamics stops experimenting and starts delivering. Meet Electric Atlas, not a prototype, not a performance robot, but a production humanoid built to operate inside real factories, handle real problems, and keep work moving when automation usually breaks down. At first glance, Electric Atlas doesn't look threatening. It's roughly human-sized, about 1.9 meters tall and weighing close to 90 kilograms, and it carries a familiar image. There are no exposed pistons, no hydraulic hoses, no aggressive or jerky movements. It stands balanced and quiet, almost understated, as if it's deliberately trying not to draw attention to itself. Also, Electric Atlas was never designed to intimidate. It was designed to fit. It moves naturally through factory between storage racks, beside carts and workstations, and next to people without forcing the environment to change around it. Factories were built for human bodies long before advanced automation existed, and every handle, shelf, doorway, and pathway reflects that. Atlas inherits that geometry instead of fighting. This is why the shape matters. Wheels struggle with steps. Fixed machines demand fences. Large systems require clearance and rigid layouts. Atlas slips into the spaces those systems can't reach. It turns where forklifts can't. It reaches where conveyors end. It stands where traditional robots were never allowed to operate. But the familiarity is misleading. Once Electric Atlas begins to move, it's clear this is not a human substitute. Its torso rotates freely. Its spine twists beyond biological limits, and its limbs articulate with a precision and range no person could safely match. The body looks familiar, but the intent is not. Beneath that calm outline is a machine built for realities humans were never meant to handle. Designed by Boston Dynamics not to look impressive, but to quietly solve problems where automation usually fails. Electric Atlas operates with 56 degrees of freedom. Every joint articulates with precision measured in fractions of a degree, allowing movement that feels deliberate rather than forceful. This is where the real transformation begins. Earlier versions of Atlas relied on hydraulics, systems that were undeniably powerful but inefficient, expensive to maintain, and difficult to scale. They consumed energy simply to stay pressurized, generated heat as a byproduct, and demanded constant servicing. Electric Atlas abandons that entire approach. In its place are direct drive electric actuators that convert power into motion with roughly 85 to 90% efficiency, extending runtime by around 30% without increasing battery size. In practical terms, this means the robot is no longer fighting its own machinery. Every movement is cleaner. Every action is more intentional. Power goes into work, not overhead. Atlas can instantly lift 50 kilograms and sustain 30 kilograms during continuous operation. Each hand can manipulate around 11 kilograms with force control, fine enough to avoid crushing delicate components. Heavy objects aren't simply picked up and dropped into place. They are aligned, stabilized, and corrected in real time as conditions change. Factories are full of imperfect parts, shifting loads, and small inconsistencies that traditional automation can't tolerate. Electric Atlas absorbs those imperfections without drama. Its strength is designed to disappear into the workflow, applied only when necessary, controlled at every moment, and focused entirely on keeping work moving. Here, the Electric Atlas moves at industrial speed. It can sprint at roughly 2.5 meters per second, fast enough to operate inside real production schedules instead of slowing them down. Its foot placement stays within 10 centimeters, even in cluttered factory environments where carts, pallets, and partial assemblies turn small mistakes into expensive downtime. Every step is deliberate, corrected continuously rather than assumed to be perfect. That control comes from the way Atlas is built. Its structure uses titanium and aluminum components optimized through advanced manufacturing techniques, including 3D printing, to place mass only where physics demands it. Nothing is oversized, nothing is wasted. This concentration of mass raises the natural control frequencies of the system, giving Atlas greater dynamic stability across a wide range of motion. The result is a machine that stays stable while moving quickly, adjusting balance in real time whether it's walking, accelerating, stopping, or even executing vertical jumps. Motion never feels cautious or fragile. It feels confident, as if the robot always knows exactly where its limits are. This is the point where Electric Atlas stops feeling like a robotic arm that happens to have legs. It becomes something else entirely. A mobile element of the factory itself. A moving piece of infrastructure that carries capability wherever it's needed, rather than forcing work to come to it. To be specific about its freedom, Atlas can rotate its torso up to 180 degrees and reverse its leg orientation without stepping away or turning its entire body. In tight industrial spaces, that matters. Instead of backing up, rerouting, or forcing the layout to accommodate it, Atlas simply reorients itself and keeps going. This freedom is multiplied by autonomy. Powered by the Jetson Thor computing platform from NVIDIA, Atlas processes an enormous volume of data in real time. It fuses inputs from LiDAR, inertial measurement units, joint encoders, and RGBD and vision into a continuously updated model of its surroundings. Model predictive control algorithms adjust balance and motion mid-stride, not after a mistake has already happened. Even during fast or aggressive movements, stability is maintained dynamically rather than enforced through caution. Atlas doesn't slow down to stay safe. It stays stable while moving at speed. It no longer waits for work to arrive within a predefined zone. It moves through the factory, carrying capability with it, adapting its body and behavior to whatever space the job demands. Its GR2 gripper prioritizes reliability over fragile dexterity. Instead of dozens of delicate fingers, it uses 3 manipulating fingers and an opposable thumb, reinforced with tactile sensors beneath elastomer fingertips. Atlas doesn't guess how much force to apply. It feels deformation, measures resistance, and adjusts its grip in real time. Objects aren't treated as ideal shapes. They're handled as they actually are. Atlas never assumes balance. When a load shifts or resists movement, the system corrects instantly, redistributing force without stopping the task. This ability to handle imbalance is what allows it to work with real industrial parts rather than perfectly staged demonstrations. That physical control is amplified by intelligence. Integrated with Gemini robotics models from Google DeepMind, Atlas understands tasks the way humans describe them. Give it a simple instruction, like moving a specific object to a specific location, and it plans the entire sequence on its own. How to approach, how to grasp, how to move, and how to adapt if something changes along the way. 2 systems operate simultaneously. A fast, low-level controller corrects torque and balance thousands of times per second, while a higher-level reasoning system interprets visual input, language, and context. One keeps the robot stable, the other decides what to do next. Together, they allow Atlas to function where scripted automation quietly breaks down. Fixed robotic cells begin to lose their relevance because work no longer has to come to a machine. Manual part sequencing fades away as heavy, repetitive handling is absorbed into a system that never tires. Forklift traffic thins out, not because it's banned, but because fewer loads need drivers in the first place. Even safety cages start to disappear, replaced by something more subtle and more powerful. Atlas operates with fenceless guarding. Its perception system continuously monitors the space around it, slowing or stopping automatically when people come too close. Padding and careful geometric design reduce pinch hazards, while its overall size and strength are deliberately calibrated for shared environments. This is not a robot designed to be isolated from humans. It is designed to work beside them. This approach is what Hyundai Motor Group calls human-centered automation. High-risk, physically exhausting, and repetitive tasks are handed to machines, while people retain judgment, supervision, and responsibility. The goal isn't replacement, it's removal of the work that breaks bodies and slows systems down. All production units for 2026 are already committed. Deployment begins at Hyundai's Savannah, Georgia facility in 2028, with a target of producing around 30,000 units annually. For most of history, strength meant muscle. Then it meant horsepower. Then it meant payload. Electric Atlas introduces a new definition. Strength is now continuous, adaptive, and programmable. It is the ability to operate without pause, learn without rest, and fit into environments never designed for machines. Boston Dynamics' Electric Atlas marks the moment humanoid robotics crossed from curiosity to capital equipment. Not because it flips or jumps, but because customers are ready to deploy it. Factories are prepared to integrate it, and the economics finally align. When humans step away, Atlas does not replace them individually. It replaces the gap they once filled. And once that gap is gone, industry does not go back.